So, good morning. In this lecture, we will concentrate on what are called as the limit theorems. That is, in asymptotic case, how do we give some prescription for the probability measure? That is why we call it as the limiting cases. They are in the limiting cases. What can you tell about the probability measure? That is one way of mentioning. Another way is, so far we looked at probability that an event or probability that a random variable taking a value in certain range is given by a value. We have been always giving the exact value of probability for certain events or for the random variable taking values in a range. So now in this lecture and in this topic, we will only be dealing with inequalities. That we will tell the probability is less than or equal to this or greater than or equal to this. So we will be only giving probability values as inequalities. That is another way of looking at it. Then we will be giving us an upper bound or sometimes lower bound for the probability. That is, probability will not exceed this or will be less than this and so on. So there are three ways of looking at it. It's all one and the same. So either we will treat it as the asymptotic case and look at the limiting probabilities, or we will give probability measures as inequalities as bounds for probability. There are various inequalities. The most popular one or the one we are going to deal with, they are the following: the Markov inequality, Chebyshev inequality, then Chernov's bound, and Jensen's it's not inequality, and then there is also Schwartz theorem. The first one is the Markov inequality. So far what happens is you have a random variable which is being characterized. Okay. If you are so interested, you can go out and look at all these. In this Markov inequality, what we will, so far the probability prescription has been given. For example, if x is a random variable, fx of x, all these things, any one of these things, if it is given, you can compute everything. All moments, everything, all statistical characteristics that we can. Then, you can, for any given event or the range over which the random variable takes a value, you can give exact values. Now, you may have a case, you know a random variable, but you don't know its probability density function, its CDF. You don't know about it. What you may at least know is some of its moments, some of its characterization, not the full characterization as the probability density function is. You may know only its mean. Okay. That is, E of x is known, which we will call it as mu. That is mu. Or you know its variance, which we will denote it as sigma square. So such things are alone being known. Again, we will see later on, just after finishing it, we will introduce certain theorems, very popular theorems. Okay, one is the law of large numbers. Okay, and then strong law of large numbers, weak law of large numbers, and then the so-called central limit theorem and so on, which allows you to get a measure. Okay, get some for this mean. Okay, the expectation using the sample mean. So it is possible that these things can be measured, but you don't yet know about the density function. So this is what it is. For example, what you have to do is you have a large population of some people, okay, and then you are just calculating the height and so on, and you only keep track of the if you keep track of the entire thing, PMF can be found out, but you only find the average value. Then in that case, this is alone you have got, and so on. So in these cases, how do we give certain bounds for the probabilities? For example, you have a case where P of x is known. Then you would like to know what is the probability that x will take a value greater than or equal to a given value. How do we guess? If you are only the mean is given, you don't know its distribution at all. There can be many density functions, it may have a given mean. Let me say if P of x is equal to 2, a continuous valued random variable, and then what is the probability that x is greater than or equal to 3? What can you tell about it? Can you make a guess? Mean is given. That gives you something. What does it give? That it is or less than or equal to 2. The probability of values taken less than or equal to 2 is equal to the probability of value taken greater than 2. That much you know for that, and we are asking about 3. So you know something, but how beyond that, how can you quantify your guess or intuition? It's difficult because you can't tell it is 1/4 or 1/3 or 1/2. It will be very difficult. For example, if you are told E of x is equal to 2, then I can have a uniform distribution between 0 to 4, which will have a mean E of x is equal to 2. This is also possible. Or I can have a Gaussian random variable with mean at 2. That's also possible. Or I can have an exponential distribution with mean at 2. Or not necessarily just one of the standard distributions. I am looking for, I want to cook up something specifically to make life difficult to answer this question, so that the mean is made as 2. So what I will do is at 2, I will draw something like that, so that this will be off, and then I can make it slowly decay like this, so that this property is off and this property is also off. If I can see that this area is off and then draw it like that, this is normalized, then also it's possible. Now the question that I am asking is, somewhere 3 is here, so I am asking these properties. So it's difficult to guess. Okay, here it will be somewhere here. So this is where these inequalities comes into picture. Well, so first in the Markov inequality, for example, how do we we will start with the formula for E of x, which is okay. Now let's look at a function u of x minus b. How does this function look like? This is how this function is. It is a step function. At a, it becomes 1. Until a, it is 0. Okay. This is how it will look like. So now E of x can be split into 2 parts. Dx. Okay. Well, now what will happen is, this is what we are doing. Okay. Whether we invoke it or not, we will see. So now in this one, well, it's an expectation. Well, this plus this is what you get expectations. Okay. So we can write this one, okay, to be yeah. So this can be written as okay, yeah. This one, this plus this is what is equal to E of x. Suppose I drop this one and then retain this. Then what I am doing? I am underpredicting, which means that E of x has to be greater than or equal to this. By dropping this, I am equating these two. It has to be like this. Okay. Now, x goes from a to infinity. Suppose instead of x, I put a, which is the minimum value it can take. Then, still I am underpredicting. So that I can write E of x is greater than or equal to a, because a onwards let x go. I am putting the least value in it. Okay. Dx. And what is this one? So they are rearranging. What we do. That is, probability that x exceeds the value a is always less than or equal to the mean E of x. So that is what the Markov inequality is.
Fx of x dx. The first term is positive.
Density function.
Oh, sorry. Before, most important thing which I have to mention that brings you this one. For random variables taking non-negative values. This is the most important restriction of the Markov inequality. It applies only to random variables which takes non-negative values. Okay? In that case, minus infinity also it will not come. Actually, it will become 0 to infinity only. Okay? Then it will become 0 to a. This is also a to infinity. It will go like that. You will see that Markov inequality has a restriction that it can only be applied for this. So in which case 0 to a you will get, that is positive. Fx of x is always positive. This is also positive. So that is for the Markov inequality. So to get what it means, this Markov inequality means something. Let's take the case where how much of utility it will have. Let's take a case that if x is not known, then okay, it gives you some idea. When x is uniform between 0 to 4, then we will tabulate the bound given by the Markov inequality and the exact value, because for this you know the exact values. You can find out because f of x is not. Then you will see how good is the inequality. provided you know the effects of x, then you can do all the evaluation of how the goodness of this inequality. Otherwise, it's not possible. So, probability that x greater than or equal to a is given by this. So, we will take different values of x and okay, I will put x here, different values of x. X is 1 by 2, sorry, x 2, 3, 4. This is the a value. Sorry. For different a values, we will compute the Markov bound and then the actual value. So what it means is that here I am asking probability that x is greater than or equal to 2 or probability that so these are what the values what the Markov inequality gives. So it is nothing but E of x by a. We know that E of x is equal to 2. So here what it should be 2, a is just whatever it is, so it is the mean divided by this value, that's all. So it is 2 by 2, this is 2 by 3, here it is 2 by 4. This is what the Markov inequality is. What it tells is, probability that x is greater than or equal to 2 is 1, 3 is 2 by 3, greater than or equal to 4 is now. Now, for x which is uniform 0 to 4, if you find the exact value and then tabulate it. Okay. For x which is uniform like that, if I ask the question, what is the probability that x is greater than or equal to 2? You know it is 1/2. Greater than or equal to 3 is 1 by 4. Greater than or equal to 4 is so, you would see that this bound is not predicting or giving a type value for your actual values. First thing is, if you look at this one, it is telling that what is the probability that x is greater than or equal to 2 is less than or equal to 1. That's what it is telling. But that is not at all needed. We know probability is always less than or equal to 1. This information is not of any great significance. Okay? And here in this case it is telling greater than or equal to 4 is less than half. But here we know it is 0 actually. So if you know the actual density functions, then of course you can criticize that it's not giving a very useful values and so on. But if you don't even know anything about it, then it is of use. For example, here I told that its only mean is 2, but I can always have some function, okay, something like this one where mean is still 2, but it can take values more than 4 also. Okay, so because you know that it is uniform between 0 to 4, you can tell it is 0 and then tell that this half is of no much use to me. But if it is something like this one which you don't even know, then telling that this probability is be less than or equal to 2, less than or equal to half means something. That is what the Markov inequality tells. Okay. Now, the next limitation of the Markov inequality is it is applicable only for random variables taking non-negative values. Okay, but random variables can take also negative values and so on. For those random variables, how do we deal? For that, we have got another equality called as the Chebyshev inequality. We will derive this Chebyshev inequality through Markov inequality. What we will do is, we will x is the random variable. Okay. We assume that two values are known to us. One is mean, another is variance. These two are given to you. It's an arbitrary random variable, then the arbitrary distributed, but mean and variance are given. Again, there are different shaped functions can be arrived at having a given mean and given variance. Okay, so mean is like this one, variance like this one, or I can also have some other form of variance. Okay, like this one. So then it can be, or it can be like this also. So we will denote it as this as mean, mu, and this as the constant, or given, or known. Then what we will do is, we will look at the random variable x minus mu the whole square. And apply Markov inequality. Inequality with this a whatever a squared also. What I am doing is, I am looking at another random variable, related random variable, which is x minus mu the whole square. For the x random variable, this is known, that is what I am going to finally talk about. But I am looking at another random, related random variable, x minus mu the whole square. And I am going to apply the Markov inequality for it. For Markov inequality, I should talk about x greater than or equal to a constant. Okay? That constant a, I conveniently am calling it as k square. But that constant a has to be a positive one. Okay? A has to be a positive. Well, now, what will happen? First, this random variable. Why I am so specific about this random variable? This random variable now is a non-negative valued random variable, because this moment I put square, it cannot take negative values. Therefore, Markov inequality can be applied. Whereas x is a generic random variable, can take positive or negative values, we cannot apply. Why was positive or important for Markov is right the question that is being asked. I cannot simply put whatever it is here. Only if it takes non-negative values, I can construct this inequality. I can drop this and construct this inequality. Look, all the line of reason. I can drop this and then construct this inequality. And then moment it is a to infinity, I can pull out x and then put it as a, which holds good. And then this is this probability, which is what we are interested in. Everything comes. We are doing gross simplification and getting bounds. Dropping this and then pulling out this a, x actually it can go up to infinity. For all of them you simply put a and then take it, and then it will still, inequality will hold good. And the rest of the one is this quantity. A to infinity fx of x is that quantity. Now, so this is what we do. So now for this quantity, random variable, what if you apply the Markov inequality? That is, not expectation on all this. What is the inequality? That's probability that x minus mu the whole square is greater than or equal to k square. Okay, and so it gives the probability of exceeding some value. It is, we will take, it gives tail probability. Probability that the random variable, it takes values greater than something. is less than or equal to E of x. E of this value, E of this modified random variable. By this, see, this is now x and k squared stands for a. And here E of that random variable we have to put. Now the random variable is modified. What is this? This one. Divided by the a. Whatever that comes here should come here. That is a square. Okay. Any question? Now, this one we can write it in a different form. X minus mu the whole squared is greater than or equal to k squared. I can alternatively write it as okay. This will hold good. Whenever x deviates from mu more than k, that is the condition. X deviates from mu more than k. If that is the case, then this will also hold. And what is this one? X minus mu the whole squared expectation. Huh? Come on. You have gone halfway in Ramayana, now I am asking who is Sita. This is sigma square. It is the second central moment. What is this? This is the second central moment. Don't always sigma squared E of x squared minus E of x whole squared. That is a derived equation. This is the definition of variance. Okay. So this is what is known as the Chebyshev inequality. We will try to make some sense out of this inequality. We will write it again. Probability that mod of x minus mu greater than or equal to k square. Now if you want, you can just sorry, k greater than or equal to k. Yeah, is equal to sigma squared by k squared. Yeah, that is important. K squared. So what it means is, suppose we have a distribution like this. This is not necessarily Gaussian. The mean can be somewhere here, mean mu, and variance may be some quantity of this one. I am looking at, okay, two variances. Okay, this is mu plus 2 sigma, this is mu minus 2 sigma. So 2 sigma, okay, I don't need not tell about sigma and all these things at this moment. We will come to that. That will be a useful interpretation. This is k. This is mu plus k, mu minus k. Then mod of x minus mu greater than or equal to k corresponds to the following area. Why we are interested is in, see, if you are given mean, if you are given variance, you know what is the likely value you will get when you do an experiment, when a realization of the random variable comes. It will be somewhere here, around mu, but it will not deviate too much of 2 sigma, 3 sigma, beyond that it will not deviate. That is what sigma means. But now we would like to know, beyond this, how much for the random variable to deviate beyond these two things is what we are looking at. Okay, extreme cases, very unlikely things, events for it to happen also. That is, we have some equipment which is supposed to work in this manner only, but for the value to deviate very much from the normal value, which may cause some events which is dangerous, lead to accident. What is the probability of having that kind of event. That is why all these things we are looking at. So what does it tell? It tells that sigma squared by k squared. For this one, probability that this will happen is so it's not equal to, it's less than or equal. That is also there. It will not exceed this one. Why again less than or equal to means this probability will be less than. Suppose I find this to be 0.95. Sorry, this will be okay 0.05 also. Then it means that this probability will be less than 0.0 or 0.005. Then you can tell that okay 0.9 it will be less than 0.00. It will be 1 by 1000 of a chance only for these events to occur. To interpret that one only we are interested. Again, what we will do is for the same case of this one itself 0. So now it need not be actually positive. Okay, x. 2 is this one. We know. Okay, is for a uniform u0 to 4. This is the f of x, and the mean is 2. Okay, and variance. What is the formula?
B minus A whole square by 12.
Uniform. This is b minus a by 2. A b means that is what this one. This one is variance of uniform. Of course, you don't need to memorize these things, but this is so important. Frequently and what it's worth also memorizing. There is nothing wrong because it is the uniform variance of uniform. This is b squared. If I am right, by 12. Am I right? Okay. B squared minus a squared by 12. So that will point out to be 16 by 12. Well, so what we are asking is, let us ask a question.
B minus A whole square.
Huh?
B minus A whole square.
Not b squared minus.
No.
B minus a जो कटेंगे. Then only this will become 16. Okay. Then what? Let us ask what is the probability that x minus mu is greater than or equal to 1, which means that we are trying to find out these areas. Always in your Chebyshev inequality, you can only ask this kind of questions. Deviation from mean beyond this value, what is the probability? That is why the shaded area will be on both this. And these areas will be equal if they are symmetric. For an arbitrary random variable, you can't tell that this area will be equal to this area. So if I am only interested in probability that x exceeds 3 is one half of this, you can't tell. But if it is symmetric, then you can tell. Is greater than. So that you know the exact value is what? What is the exact value? 1 by 2. Because this is 1, this is 3. I am asking, these are all squares. This plus this will be 1 by 2. What does Chebyshev inequality gives? So probability that mod of x minus 1 mu is 2 is greater than or equal to 1. That is less than or equal to. This is less than or equal to sigma squared by k squared. Sigma squared is 16 by 12 divided by 1 squared. Okay. Is this an interesting result? No. 16 by 12 is greater than 1. I am telling probability is greater than some value 1.7. It's not useful. But if you don't know anything about it, then it can be of some use. For example, I can also have Okay, I don't know, but maybe another rectangular function mean I can always make it 2, but variance of 16 by 12 I am not very sure. If I keep the area 1 and then expand it, variance can become different, but near to that I can always keep it, but see to that it exceeds 4, that I can always do. Okay. So that is about the Chebyshev inequality. We will also look at something more. Let's look at an exponential random variable. Lambda that is equal to 1. For this we will try to apply the Chebyshev inequality. So what is this one? How does it look like? Lambda e power of so lambda is 1, it is e power of minus x only. That is the plot. It starts from at 0, it starts from 1 and then it decreases like this. And what is the mean? Of exponential random variable parameter lambda? 1 over 1. Variance
1 over lambda square.
It's also 1 over lambda. Something somewhere in here. Something is 1 over lambda. Variance is also 1. So mean is somewhere here. So we will ask what is the probability that we'll ask to get some
Lambda square.
1 by lambda square.
Yes, sir.
Okay, that's how to equal to. Yeah, probably it will be 2 by lambda. Second is 2 by
2 by
lambda
lambda
square and the minus 1 over lambda square is 1 over lambda square. Now if you ask this question, okay, should be Monroe inequality, Chebyshev will give you something, but what is the physical interpretation of this? That is, x deviates from the mean, which is 1, by a value more than 1. That is, it is 1 on this side below 1 on this side and above 1 on this side. It is below 0 and above 2. But incidentally, you know that expo random variable is non-negative. So this property is 0 and this is the only thing shaded area which will contribute. So safely we are trying to find out what is the probability that x is greater than 2. This tail probability is what we are asking. Is less than or equal to sigma squared by k squared. So that is what sigma squared is 1 divided by k squared is that yeah 1 is what it gives. If you want, we can give. You can also make it little this one. If you want, you can make that is equal to See, if you change the value, you have to easily change this one. Sorry, is greater than or equal to 4. It will become like this. Okay? Like this is something which is okay, it's useful because 2 on this side it did not happen, of course. But 2 on this side, what I am asking is from 3, it will become 3 from 1. I know something exists. I don't know what will be this property, but this tells you that it is less than 1. That is of course of some use to me. But actually we can find these exact values. What is this one? In this case, this one happens to be probability that x is greater than or equal to 2. Okay? And that is nothing but this CDF evaluated at 2, or Poisson CDF evaluated at 2. Right? What is that? 1 minus e power of minus lambda. Oh, CCDF, correct. Of course, yeah. It's a CCDF. So, greater than or equal to 1 minus fx. That is e power of minus lambda x. E power of minus 2. Okay. So what is this? This is 1 over e squared. What will be e squared roughly? Around 10. Little more than 10, right?
6
No,
to 7.
2.7 or something. So it will be 0.15, something of that kind. 0.15 or this one. For this one it is telling 1, which is not of this one. Even if it is 2, e power of minus 4, that will be even lesser quantities. But this is predicting 1 by 4. So you can compare the exact value with the bound and then check how good it is. But imagine only thing is, if you know all these things, you can do so you can talk big about it and so on. If you don't know anything about it, then these bounds are of some use. Yes. Then we have one more thing. There is a Chernow's bound which will take some time. Take it later. Jensen's inequality. Okay. So what we will do is we will consider. See, sometimes what we do is we have a formula. We want to find actually some. Or we will not something like this. X power n plus 3 and so on, where the n is a random variable. It's a non-negative integer valued random variable. Because of this may be a function, it's a variable, that's all. Because of that one, this becomes a random one, because n is random. You want to find, okay, or x is also given, also or 2 power n, let us say make it like this, 2 power n plus 3. So it's a function of n. n is a random variable and you know how it's the density function, everything is being given to you. Then you want to find what is the expected value of this. How do we find it? N is a random variable. You know its density PMF, which will allow you to find expected value of n. I want to find the expected value of f of n. How do I find it? Can I put 2 power e of n plus 3? I find what will be the expected value I am doing. N is a random variable. So what is the expected value n will take, and that I will plug it here and then evaluate this function. Will that be the expected value of f? It won't be. But this is the usual mistake many will tend to do. Okay, n, what is the likely value? If I know n, I will know it is n is 2 means I know it is 2 4 plus 3 7. That is 7 is what is going to happen. But I don't know. So can we put it like this one? You don't know. So f of n is it equal to f of e of n? It is in general not correct. If it is a linear function, then it is correct. Okay, 2n plus 3 means expectation. If you take expectation over 2 into e of n plus 3, linear function is true. For any complicated function, is not true. If I put y is equal to sin x, sin theta, theta uniform between some value 0 to 5. Okay, its expected value is pi by 2. Then that does not mean that, okay, you can put this one and then tell the expected value of y is 1. Because it's not a linear function, it's a complicated one. So these things generally arise. So what this tells is, if you have functions g of x, okay, which is convex in a domain, say x1, x2, between x1 and x2, it means that between some x1 and x2, if you plot g of x versus x, it's of this one. It is of this kind. Then, if you evaluate g double dash of x, what can you tell about it? The first will always be greater than or equal to 0 in this domain. Huh? Is it right? Greater than or equal to 0. Then what we will do is, we know the Taylor's expansion of g of x at x equals to a value a. That is g of a plus x minus a into g of x, g dash of x at x equal to a plus whole square by maybe by 2 factorial will come.
Yes.
2 factorial g double dash of x plus anything. But now what will happen is, here, see, is this right? So why I am looking at convex, because x minus a the whole square is positive, and this convex nature guarantees that g double dash of x is also positive. Both are positive. So what I am doing is, there is some positive quantity and all these are supposed to be lesser than this for x closer to a. So if I drop this, then what I am doing is I am underestimating. Then I can tell g of x, okay, is greater than or equal to x, not x equal to a, g of x is greater than or equal to g of a plus x minus a into g dash of x. I can tell it because I am dropping this one. If we don't drop, this will be larger. After dropping, this will be higher. I can write it like this, under these conditions. Now, we will evaluate x. Okay, we will keep a is equal to e of x. I can expand it around any value a. I will expand it around e of x. Then I will take expectation probe e of g of x is greater than or equal to e of g of a is just g of a, where g of a is plus x. It is expectation e of x minus a into g dash of x. First I will invoke this later. I am just taking expectation. Is it okay? E of g of x is greater than or equal to e of g of a plus e of x minus a. I will expand it around this one. In which case you will have e of g of x is greater than or equal to, this becomes 0. E of not expectation of g of this one. So what will happen is now it is actually g of a is a constant. But what is the value? A is now, see, once you put a, g of a is a constant. So expectation will simply give you g of a, but a is e of x. So this is what we get. So what this inequality tells is for a convex function, okay, if you have a function of the random variable, the expected value of the function is always greater than or equal to the function evaluated at its mean. That is what it tells. It is not equal, but this will be greater than this. That is what the Jensen's inequality tells. We'll stop at this point.